I'm Ali. Have you ever wondered how these robotic vacuum cleaners work? Well, today's question is about that. Also, this question has been asked by Amazon, Google, and Facebook. The name of this question is Robot Room Cleaner, which is a challenging question. But don't worry, we will solve it together. Now, let's take a look at it.
The question says, given a robot cleaner in a room modeled as a grid. So consider this is the grid that we have, that it shows our room. Okay, so this is the grid that we have. And it says that each cell in the grid can be empty or blocked. So for example, this cell is empty or this cell is blocked. And the robot cleaner with 4 given APIs here can move forward, turn left, or turn right. Okay, and each turn it made is 90 degrees. So for example, now if my robot is here, with these calls, I can move forward or turn left or right. And if this is the direction that the robot has now, when we call turn right or left, it just turn with 90 degrees. So the new direction would be this. And when it tries to move into a blocked cell like this, its bumper sensor detects the obstacle and it stays on the current cell. So consider the robot is here and it is moving toward this direction. So as this cell is blocked, it cannot go there, so it just stays in this cell. Okay, so we have to design an algorithm to clean the entire room with these APIs that we have here. So let's take a look at them. In the robot interface, we have 4 methods. The first one is a Boolean method, and it's called moved. So it says that it returns true if the next cell is open and robot moves into the cell. So if my robot is here, for example, the robot is here, and this is the direction. So the move method will return true if the next cell is empty, and the robot can, which means the robot can move there. And when I call move, it returns true, and the robot will be there on the next call. And it returns false if the next cell is obstacle or is blocked, and robot stays on the current cell, like here. The next cell is an obstacle or is blocked, so the robot cannot move, and also the move method returns false. Then we have turn left, and turn right methods. So it says that robot will stay on the same cell after calling turn left or right. So if this is our robot and I call, for example, turn right, it won't turn right, move to this. It just stays on the current cell and its direction will go right. For example, if it's going toward this direction and I call turn right, the new direction would be this. Or if the direction is this and I call turn left, the new direction will be this. So yeah, and 90 degrees that we have talked before. And also we have a method called clean to clean that cell. So when we call that, when we are here, I mean when the robot is here and we call clean, it means that this cell has been cleaned. The problem also gave us an example to show us the input format. So as you can see, the room is a 2D array, contains several ones and zeros. The ones show the empty cells of this grid, and the zeros show the blocked ones. It also gave us the starting position of the robots. And there are also several points that we should consider while solving this problem. The first one is that this problem is a blindfolded problem. And it means that at the beginning, our robot is not aware of the whole map or all the blocked cells or empty cells. And we just can control our robot using those those 4 APIs that we've seen earlier. And also the robot's initial position will always be in an accessible cell. So it is not on a blocked cell or somewhere that we cannot access that. And the initial direction of the robot is facing up. So this is important too. And all accessible cells are connected. So as you can see here, the ones which are the accessible or empty cells are all connected. So for example, if here instead of 1 we have 0, we had series of empty cells here and blocked cells here, and these two empty cells, I mean these two sections of empty cells would be separated. But according to the 4th point, we don't have such a thing in our map. And we also should assume that all 4 edges of the grid are surrounded by a wall. So around all these 4 edges, which shows the map, there is a wall or there is blocked cells. Now that we understood the problem, let's talk about the suitable algorithm to solve this problem. The algorithm that I want to explain is called spiral backtracking. And this algorithm is based on 2 programming concepts. The first one is backtracking and the second one is constrained programming. Now let's take a look at what are these concepts mean. So in order to explain backtracking, assume that these are the blocked cells in our grid. And also our robot initial position is here and its direction is right. So when I move to the new cell, which is here, you can see that this our robot is trapped here among 3 blocked cells and 1 visited cell. So we need something to go back to the previous cell and choose an alternative path instead of this path. So this is called backtracking. And constrained programming means that we mark visited cells as obstacles, or better to say virtual obstacles. So if I've been there, or better to say if our robot was there before, when our robot moves to the next cell, which is here, it should see this cell also as an obstacle. Although it's not an actual obstacle, but it should behave this cell like an obstacle. So when it is analyzing the path around itself, it should say, okay, I cannot go there because it's an obstacle too. But the difference is we can backtrack to visited cells. So instead of going back or saying to move to this cell, we say we backtrack to itself, and then from this cell, for example, we find another path or an alternative path. For example, we can choose to go here and continue our path. Pay attention that in this problem, we consider the initial position of the robot as origin of our coordinate. So if this is the initial position of our robot, we will take this as 0, 0. And also keep in mind that our coordinate is something like this. So if here is 0, 0, then here would be -1, here is 0, 1, 2, and here would be -2, -1, 0, 1, 2, 3, and 4. For this problem, we need a prioritization system for robots' movement, and it will help us in facing obstacles. So consider that our robot is here. Consider our robot is here, and this is its direction. Its direction is right, and here is an obstacle. So what should the robot do in this situation? I mean, which direction should it choose instead of this direction? So we need an alternative direction or a plan. And I use the right-hand rule, which is used in maze solving too, as a plan for our robot movement. So our first direction is up, and if we face any blocked cells in up, we turn right. So then we have right. And if we face an obstacle in right, we turn right again, and then we have down, and then we have left. So keeping that in mind, let's see an example together to understand this algorithm. So consider this is the initial position of the robot, and as the problem says, the initial direction of the robot is up. So we start our movement. The robot goes up, and still its direction is up, but it sees that here's an obstacle, so it cannot move there. So based on the right-hand rule that I just discussed, it should turn right, and this is the new direction. But there's an obstacle too, and so it turned into down, and there is a visited cell, which is a virtual obstacle, and then it turned right again, and the new direction is left, and it says, okay, here's empty, so it goes left with this direction. It is empty, so it continues its movement. Then there is a blocked cell again, so it turns right, and it sees up direction. It is blocked, right, it is visited or blocked, and down, it's empty. So it goes down, and it continues to goes down, and then again down. But here is an obstacle again, so it turn right, so the new direction is left. It's blocked, here is blocked, and here is empty, so it goes right. And it continues to go right till it faces an obstacle. Again, an obstacle, and then here is obstacle, here is obstacle, blocked, so it can just goes up. So it chooses the up direction and goes up till again it's faces an obstacle. Okay, here is an obstacle, so, and right is obstacle, down is obstacle. It can just go to left, so it goes to left, and again we have an obstacle. So an up is blocked, right is blocked, down and left are both blocked. So as you can see, all four directions are blocked, and here we should backtrack. So we backtrack to the previous cell, which is here, and try to find an alternative path or alternative direction from that cell. So here our direction was left. We turn right, and we, again, based on the right-hand rule, we analyze all directions to see, do we have an alternative or path or not. So up is blocked, right is blocked, but down is a good one. So this is our new direction, and it goes down. Again, this is blocked, so it turned right, and the new direction is left, and it goes left. Again, it's blocked, up is blocked, right is blocked, and down is blocked. So it should, again, backtrack to the previous cell. And when it backtracks, it sees that all around is blocked, so it backtracks again. Backtrack, 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 backtrack. So as you can see, because all of these cells are rounded by blocked cells, so we have to backtrack till we find an empty cell. So we backtrack here, 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 and here. As you can see, we have an empty cell here. So, and the direction here was right. So we see, or the robot sees down, it is blocked, left is blocked, but up is empty. So it chooses up, and it goes up. Again, up is blocked, right is blocked, down is blocked. So the new direction would be left, goes left, but it's blocked. So it turned right, and the new direction will be up. It goes up, up is blocked, right is blocked, down and left are both blocked. So we backtrack here, then we have here, we backtrack here, we backtrack here, and here, and here, here. So we don't have any other empty cell. So we are searching for empty cells, and we backtrack all along this way. Sorry, that was a mistake. So we backtrack here, and from here, here, and this is the initial point that we had. So we turn back to the initial point. But as you can see, we have an unvisited cell yet. So it goes there to clean that cell too. The robot is surrounded by all blocked cells, so it backtracks here, and there is not any other empty cells that it can go. And here is the place that the algorithm stops. Okay, so now that we've seen the algorithm in an example, let's talk about something that will be used in code, I mean in the next section. So based on the right-hand rule, and also keep in mind that the coordinate that we have are in this way, and considering that this is x and this is y, we have to write several math equations for these directions. So when we goes up, it means that, for example, if we are here and we goes up, it means that the y is constant, but x will be decreased by 1, right? So the new position would be x minus 1 and y. And when we go right, as here, you can see, when we go right, the x will be the same, but y will be increased by 1. And when we goes down, so here, sorry, that was bad. So yeah, it is more beautiful. When we goes here, we should increase x by 1, and the y will be the same. And left, when we goes left, the x will be the same, but y will decrease by 1. So we use these positions in our code, so it's important to understand them, and also pay attention that the coordinate that we use is a bit different from what we usually have. And now that we understood the algorithm and how it works, let's see and analyze the suitable code for this algorithm. The code contains robot interface that the question gave us, and the solution class that we wrote. In solution class, we have 3 methods: go back, backtrack, and clean room. So the program starts from clean room that takes a robot object, and then it calls backtrack with the initial position and direction. Before I explain backtrack, I should say that we assign a specific number to each of these directions. So we assign 0 to up, 1 to right, 2 to down, and 3 to left. So direction 0 means up, as the question says that the initial direction of the robot is up. Now let's see backtrack. Backtrack takes 3 parameters, x, y, and the direction. And the main movement of the robot happens here. First of all, we add the current position of the robot to the visited. Visited is a hash set that we have for visited cells of the grid. Then we clean that cell with robot.clean, which is a method in robot interface. Then we have a for loop. In this for loop, we first assign the current x and y to the new x and y of the robot, and then we specify the new direction of the robot using this formula. And let me explain this formula a bit. dir is the current direction of the robot, and consider this is up right now, so it is 0. And consider also I is 2. So we add them together, and this mod 4 will equals to 2 again. So the new direction would be down. And the reason we add mode 4 is that, for example, if the direction equals to 3, which means left, and the I equals to 3, the new direction would be 6 that we don't have in our numbers. So we use a mod for to assure that the new direction is in this range. Then we check the new direction for new positions of the robot based on this equations that we had here. So if the new direction equals to 0, it means that the direction is up, and based on this formula we decrease x by 1. And if it is 1, which means right, we increase y by 1, as you can see. And if it equals to 2, which means down, we increment x by 1. And finally, if it equals to 3, which means left, we decrease y by 1. Then we have an if statement for robot movement. And in this if statement, we check if the next cell with the new x and new y is not in the visited hash set, and also robot can move there. Again, move is a method in the robot interface that the question gave us, as you can see here. So if the robot has both of these conditions, we call backtrack for moving, for the movement of the robot. So the robot goes and find new direction and new position to go there. And also pay attention that this is a recursive call. And in this recursive call, we find new cells and new paths for the robot. And when it hits an obstacle, it exists from backtrack. And what should we do next is to go back. So let me show you by an example to better understand it. Consider that our robot is in a cell like that, and here is a blocked cell, and also here, and also here. So this robot is surrounded by all blocked cells, and the backtrack cannot find any new way for that. So we should go back to the previous cell to find an alternative path from there. And in order to do so, we should change the direction of the robot and goes there. So what do we need is to call turn right twice. So the direction would be inverted, and then we call move. As you can see here, I called turn right twice and called move to move the robot to the previous cell. And we should invert the current direction to the prior direction to find the new path. So we again call turn right twice, and this will give us this direction, which is the prior direction of the robot in the last cell. And at the end of this for loop, we call robot.turn right for the new direction in order to find the new path. Now let's submit the code into LeetCode.com and see the results. So first I run the code. So it's accepted, and now let's submit that. So as you can see, as our code was successful, and our code is faster than about 100% of Java Online submissions for this problem, and also our memory usage is less than 97% of Java Online submissions for this problem. So we have done a great job. Now let's talk about the time and space complexity of this algorithm. If we consider that n is the total number of the cells that we have in a grid, and m is the number of blocked cells, so the time complexity would be an order of n minus m, because we iterate through each each available cell, I should say, once. So this is the time complexity that we have. And also the space complexity is the same, because we have used a hash table for visited cells, which is again n minus m.